For 4,500 years, the Great Pyramid has guarded its greatest secret. How did ancient builders, without modern machinery, lift millions of stone blocks to create a perfect geometric mountain? The answer has remained one of history's most stubborn puzzles, defying explanation and spawning countless myths. But a revolutionary idea, known as the internal ramp theory, is finally changing the game. By the end of this, you will understand the elegant, human-scale blueprint that makes this impossible feat not only possible but brilliantly logical. We will uncover the hidden corridor predicted by an architect, examine the startling scientific scans that back it up, and see how this single concept redefines an entire civilization's genius. What does it truly mean to solve a mystery that has stood since the dawn of recorded history? Think about a single stone block, a piece of solid limestone the size of a small truck. Now multiply that by 2.3 million. That is the raw physical reality of the Great Pyramid, a mountain assembled block by block, each one lifted hundreds of feet into the sky. For centuries, the most logical explanation seemed to be the one right in front of us. Builders must have constructed gigantic external ramps, earthen or brick roadways that grew taller as the pyramid did, allowing workers to drag those immense stones upward. It is a straightforward image, one that makes intuitive sense. But when you actually run the numbers, this classic theory collapses under its own impossible weight. To raise stones to the very top, a single straight ramp would need to be over a mile long. Building a ramp that massive would have required more material than the entire pyramid it was meant to construct. Then, after the final block was set, you would face another monumental task. How do you dismantle a mountain of rubble and brick without leaving a single trace? Where did all that ramp material go? This is the central paradox that has haunted Egyptology for generations. The ambition of the pyramid builders is undeniable, but the proposed method creates a problem just as large as the solution it offers. This glaring logistical flaw is the very reason our search must look elsewhere, not at the landscape around the pyramid, but deep within its stone heart. The answer was not in the sand, but in the stone. It arrived not through a traditional excavation, but through a digital one, born from the mind of a man trained to think in 3 dimensions. Jean-Pierre Houdin was a French architect, a problem solver by profession, and he brought a radically different toolkit to this ancient mystery. While others studied pottery shards and hieroglyphs, Houdin opened a 3D modeling program. He did not see a tomb or a symbol of power. He saw a construction site. He approached the Great Pyramid with the same practical mindset he would use for a modern skyscraper, asking a brutally simple question that had somehow eluded centuries of study. What if the builders never removed the ramp because they never built it outside in the first place? What if the ramp was inside the pyramid all along? This single thought was a paradigm shift. It reframed the entire challenge. Instead of an external, temporary structure that created more problems than it solved, Houdin proposed that the ramp was a permanent, integral part of the pyramid's design, a hidden highway spiraling upward within the monument's own walls. This was not a vague speculation. Using his architectural software, Houdin began constructing a detailed, testable model. He worked out the precise angles, the turning radii for sledges carrying multi-ton blocks, the internal corridors needed for ventilation and worker passage. He visualized how the builders could have used the pyramid's own growing structure as a scaffold, building the ramp as they went, sealing it behind them as they ascended. This was a blueprint, a step-by-step construction manual derived from logic and engineering principles, not legend. It was a modern mind using contemporary technology to finally listen to the whispers of an ancient one, proving that sometimes to see the past clearly, you need to look at it through a completely new lens. The brilliance of Houdin's spiral lies in its elegant simplicity. Picture a parking garage, but one built 4.5 millennia ago. Instead of cars, it was designed for teams of workers hauling immense stone blocks on wooden sledges. The core principle is a continuous, ascending corridor that spirals upward, tucked just inside the pyramid's future outer skin. As each new level of the pyramid was completed, builders would extend this internal ramp another turn, always maintaining a gentle, manageable slope. The ramp itself became the construction road, a permanent feature growing in perfect sync with the monument. This solves the colossal waste problem instantly. There is no separate mountain of ramp material to build and then mysteriously vanish because the ramp is the pyramid. Its walls are the pyramid's internal structure. This internal highway also provided a stable, enclosed environment. Workers were shielded from the desert wind and sun, and the consistent, engineered slope made the grueling task of dragging multi-ton blocks a matter of endurance, not impossible physics. The pyramid, in this view, was not just a tomb being built. It was its own construction site, a machine for building itself, with this hidden spiral corridor serving as its functional spine. Every block from the foundation to the capstone traveled this same interior path, a journey from the desert floor to the sky, sealed in stone behind it. This foundational logic turns the pyramid from a static mystery into a dynamic process, a snapshot of an ingenious construction method frozen in time for us to decode. But a blueprint in a computer needs proof in the real world. Houdin's theory made a startlingly specific prediction. If an internal spiral ramp existed, there must have been a way to get the blocks from that internal corridor out onto the pyramid's outer surface as each level was built. The stones could not spiral upward forever. They needed exit points. His three-dimensional model pinpointed where these crucial transfer points would logically be located, at each of the pyramid's four corners. And then he went looking for evidence, high up on the northeast corner of the Great Pyramid, where the original smooth casing stones still cling to the core. There is a peculiar feature. It is a deep, squared-off indentation, a distinct notch cut right into the structure. For most of modern history, this was dismissed as simple damage, perhaps erosion or the result of later stone removal. But through the lens of the internal ramp theory, this notch transforms into something far more significant. It becomes a construction dock. Picture this corner left deliberately open during the build. Teams inside the dark, ascending corridor would haul a block up the internal ramp. When they reached the correct level, they would not turn another tight corner. Instead, they would guide the massive sledge straight out through this open notch, pivoting it 90 degrees onto the fresh, waiting surface of that pyramid level. This open corner was a loading bay, a planned architectural feature designed for a single, repetitive task. The notch is not an accident of time. It is a fossilized instruction, a permanent record of a workflow that was repeated thousands of times. It is the silent, physical signature of a process, etched into the stone for anyone who knows how to look. Yet the most compelling evidence for a hidden interior would not come from the surface, but from a silent rain of cosmic particles. In 2017, an international team of scientists launched the ScanPyramids mission, a project dedicated to seeing through stone without ever touching a single block. They employed a technique called Muon tomography, which sounds like science fiction but is grounded in remarkable physics. Muons are subatomic particles created high in the atmosphere, and they shower down upon us constantly, passing effortlessly through solid matter like ghosts. By placing sensitive detectors around the pyramid's base, scientists could track the density of these passing muons. Where more muons passed through, it indicated less stone, meaning a hidden chamber or corridor. It was a way to take an X-ray of a mountain, and what they found sent shockwaves through the world of archaeology. The scans revealed a massive, previously unknown void deep within the pyramid structure, located directly above the famous Grand Gallery. Researchers cautiously named it the Big Void. This was not a small crack or a natural fissure. It was a deliberate, architecturally significant space over 100 feet long. While the team was careful not to declare it proof of any specific theory, the existence of this large, hidden compartment was a seismic piece of data. For Jean-Pierre Houdin, it was a moment of profound validation. His detailed 3D model, created years before this scan, had always included large internal spaces and corridors necessary for the logistics of the internal ramp system. The discovery of the Big Void did not just reveal an empty space, it revealed a pattern. It showed that the pyramid's interior was not a solid mass, but a complex, engineered structure with purpose-built cavities. Modern physics, peering across millennia, had detected the echo of an ancient architect's plan, offering a powerful, scientific whisper that the internal blueprint might be real after all. The Grand Gallery is one of the most breathtaking spaces ever carved by human hands. For over a century, visitors have stood in awe of its soaring, corbelled ceiling, a masterpiece of precision that seems to pull the eye upward toward the heart of the pyramid. It has always been interpreted as a processional way, a grand architectural statement leading to the final resting place of the king. But what if its true purpose was far more practical and even more brilliant? Jean-Pierre Houdin looked at this iconic corridor and saw something entirely different. He saw a machine. In his model, the Grand Gallery is not a ceremonial endpoint. It is the beating heart of the construction process, a grand hauling chamber designed to solve the single most difficult lifting challenge of the entire project. The king's chamber sits deep within the pyramid's core, and its ceiling is made from enormous granite beams, each one weighing over 50 tons. How do you lift a stone the weight of a locomotive hundreds of feet into the air and then slide it perfectly into place? An external ramp, even an internal spiral, would struggle with such a specific heavy load. Houdin's answer lies in the gallery's unique design. Its steep, smooth floor and high walls are perfectly suited for a sophisticated counterweight system. Imagine a giant sled carrying one of these granite beams, positioned at the bottom of the gallery's incline. Ropes from this sled would run up and over a pulley system at the top of the gallery, then back down to a separate container holding heavy granite plugs within a shaft. By slowly filling this container with more plugs, the increasing weight on one end would gently, controllably pull the massive beam up the gallery's slick limestone floor. It is a simple principle of physics scaled to a monumental degree. This transforms our understanding completely. The Grand Gallery is no longer just a beautiful hallway. It becomes a permanent installation, a built-in crane that was used to assemble the pyramid's most critical internal component. Once its work was done, this ingenious machinery was simply left in place, becoming the majestic space we marvel at today. The most sacred room in Egypt was literally built by the corridor that leads to it, a perfect fusion of practical engineering and eternal purpose. This step-by-step process reveals a masterclass in ancient project management. The builders did not simply start piling stones. They executed a phased, evolving plan that adapted the construction method to the growing challenge. The journey began with a traditional, straight external ramp built from compacted earth and rubble. This was the sensible starting point, an efficient way to move the immense volume of stone needed for the massive foundation and the lower third of the structure. Think of it as the project's initial staging ground where the rhythm of work was established. Teams could haul blocks along this direct, open pathway, building upward layer by layer. But this external ramp had a built-in expiration date. As the pyramid grew taller, the ramp would need to grow longer and more massive, becoming its own engineering nightmare. The ancient foremen knew this limit was approaching. Their genius was in planning the transition long before they reached it. While workers were still using the external ramp, others were already busy inside, constructing the beginning of the internal spiral within the pyramid's own growing core. They were building the future highway even as they used the old road. At around 43 meters high, the moment arrived, the external ramp had served its purpose. Now the focus shifted entirely inward. The open desert worksite transformed into a contained, focused operation. Teams now guided their heavy sledges into the mouth of the internal corridor, a dark, sloping tunnel that curved gently upward within the safety of the stone walls. The outside world vanished, replaced by the echo of effort and the smell of rope and stone. This was no longer about building a ramp. They were now building within the ramp, their path forward defined by the very monument they were creating. At precise intervals, a burst of sunlight would mark a corner. Here, a section of the outer casing was left temporarily open, creating that crucial loading notch. Workers would maneuver a block out of the tunnel's darkness, pivot it on wooden rollers, and set it perfectly into position on the pyramid's fresh, unfinished face. Then they would seal that opening with a casing stone, and the internal corridor would continue its spiral ascent, leaving a smooth, seamless side behind them. The pyramid was quite literally growing and sealing itself shut in a single, continuous, breathtaking operation. The real challenge was not just moving the stone, but managing the movement itself. Inside that dark, spiraling corridor, a chaotic free-for-all would have meant disaster. This was not a simple tunnel. It was a precision-engineered highway operating under the crushing pressure of time and gravity. The internal ramp theory provides a surprisingly modern solution. It suggests the builders implemented a strict one-way traffic system. Picture two parallel tracks running along the corridor's floor. On one side, teams of workers would strain against ropes, hauling a massive, stone-laden wooden sledge up the gentle incline. Their progress would be slow, methodical, a testament to coordinated effort. On the other side, moving in the opposite direction, would be the empty sledges. Having delivered their cargo at a loading notch, they would now be guided back down to the base, ready for another load. This separation of ascent and descent is a fundamental principle of logistics. It prevents catastrophic gridlock in a confined space, ensuring a continuous, rhythmic flow of materials. The smooth limestone floor, perhaps even subtly grooved or lubricated with water, would have made this back and forth possible, turning an impossible crush into a controlled, circulating system. But moving stone is one thing, moving people is another. Dozens of laborers working in shifts for decades in a sealed, ascending tunnel would have faced another invisible enemy. The air itself would have grown thick and stale. This is where another famous feature of the Great Pyramid finds a startlingly practical purpose. The narrow, mysterious shafts that run from the king's chamber out to the pyramid's exterior have long been tied to spiritual beliefs, seen as pathways for the soul. Yet from a construction manager's perspective, they serve a vital, immediate function. They are ventilation ducts. By creating these narrow channels, the builders engineered a passive airflow system. Fresh desert air could be drawn in from the base, rising through the internal corridors as they warmed, while stale air was vented out through these higher shafts. It was an ancient answer to a critical workplace safety issue, ensuring that the human engine at the heart of this project could keep breathing, keep working. When you view it through this lens, the Great Pyramid undergoes a profound transformation. It ceases to be a static mountain of rock. Instead, it reveals itself as a dynamic, living system. It was a closed-loop factory, a monument that functioned as its own supply chain, its own traffic control center, and its own environmental system. This logistical framework showcases a level of operational planning and efficiency we often believe was invented centuries later. The pyramid builders were not just master stonecutters. They were the world's first great project managers, orchestrating a symphony of labor, material, and time on a scale that still defies belief. Every revolutionary idea must stand in the crucible of scrutiny, and the internal ramp theory is no exception. For all its elegant logic, it has faced pointed questions from the archaeological community. The most common challenge is a direct one. If this spiraling corridor existed, where is the physical proof? We should see its walls, its floor, the clear archaeological footprint of a tunnel built within the pyramid's core. Critics rightly point out that no such definitive corridor has been found. The rebuttal to this lies in the very nature of the construction method. The internal ramp was not a separate, permanent feature like the Grand Gallery. It was a temporary workspace, a construction chute. Once a section of the pyramid's outer casing stones were placed from the inside, the builders would have immediately backfilled the now useless ramp segment with loose rubble and smaller blocks, turning it into solid core masonry. The ramp did not vanish, it was transformed. Its walls became the pyramid's own internal fabric, its path now just a chaotic jumble of stone within the monument's heart. We are not looking for a clean, hollow corridor. We are looking for a specific pattern of construction debris, a spiraling vein of smaller material within the larger blockwork. This pattern has not yet been conclusively identified, but it is a needle in a 2.3 million block haystack. Another practical concern involves the turns. Could a team of workers really maneuver a sledge carrying a multi-ton block around the tight, 90-degree corner at each loading notch? It seems like a recipe for jamming, for snapped ropes, for impossible friction. Yet here, the theory draws strength from a simple, often overlooked technology. The ancient Egyptians were masters of woodworking and lubrication. We know they used wooden rollers and likely poured water or a slurry of wet clay on the ramp surfaces to drastically reduce friction. A block on a lubricated sledge pivoting on greased wooden rollers at a corner becomes a manageable physics problem rather than an insurmountable obstacle. It would require skill and coordination, yes, but not magic. The notch itself provides the necessary space for this precise maneuver, a built-in pivot point that turns a sharp corner into a controlled, repeatable procedure. What gives this idea its compelling weight is not that it answers every single question with absolute proof. It is that it provides a single, cohesive system that explains a constellation of mysteries that other theories treat in isolation. The mysterious notch in the corner, the purpose of the Grand Gallery, the need for the so-called ventilation shafts, the complete absence of external ramp debris. The discovery of the Big Void. Traditional explanations often address one or two of these puzzles, leaving the others hanging. The internal ramp theory connects them all into a single, logical narrative of construction. It treats the pyramid not as a collection of unrelated features, but as an integrated machine where every part served a purpose in the build. This holistic power is its greatest strength. It feels like seeing the blueprint for the first time, where once we only saw a bewildering collection of walls and chambers. The critics keep the conversation honest, demanding evidence and rigor. But the theory answers by painting a complete picture that makes the impossible suddenly, brilliantly plausible. Those granite beams above the king's chamber are a problem that defies gravity. Each one is a slab of solid rock weighing as much as a small blue whale, lifted hundreds of feet into the air and then slid into a perfect hairline slot. How do you even begin to approach such a task with only ropes, wood, and human muscle? The internal ramp theory offers a breathtakingly direct answer. Those beams did not descend from the sky. They traveled the same hidden highway as every other stone. They were hauled up the internal spiral, one agonizing turn at a time, until they reached the very top of the ramp system. But their journey did not end there. The final destination for these titanic blocks explains the pyramid's most enigmatic architectural puzzle. Directly above the king's chamber sits a stack of 5 small, empty rooms known as the relieving chambers. For over a century, their official purpose has been straightforward. They are a structural cleverness designed to divert the unimaginable weight of the pyramid's peak away from the flat ceiling of the chamber below, preventing it from collapsing like a house of cards. This is true, but it may only be half the story. In Houdin's model, these chambers were not just passive supports. They were an active construction zone, the grand finale of the internal ramp. Think of this space as the ultimate loading dock. After a granite beam completed its long, spiraling ascent, it would emerge into this open, multi-level area at the pyramid's apex. Here, in a controlled environment shielded from the desert winds, workers could perform the delicate final maneuvers. Using levers, ropes, and precisely placed timbers, they could pivot each beam from its horizontal travel position into a vertical alignment, then slowly, carefully lower it down into its permanent home atop the king's chamber. The 5 chambers in this view are the architectural footprint of that complex operation. Their stepped, compartmentalized design provided the necessary space and multiple anchor points for the ropes and counterweights needed to handle such massive objects with precision. Once all the beams were set, this entire upper workspace, its job complete, was simply sealed off. What we call the relieving chambers, then, might be better understood as the construction cockpit. They are the silent, empty evidence of the project's most audacious lift, a built-in crane housing that was left in place as a permanent part of the monument's support structure. This single interpretation solves 2 profound mysteries at once. It explains how the beams got there, and it gives a brilliant, practical reason for one of the pyramid's strangest internal features. The genius of the builders shines through not in the mystical, but in the magnificently practical. They designed a machine that, once its work was done, would vanish into the very fabric of its own creation, leaving behind only awe and a trail of clues for the future to find. The elegance of the internal ramp becomes undeniable when held against the alternatives. For centuries, the debate has centered on one question: what is the most efficient way to build a mountain? The external straight ramp, the classic image, fails its own efficiency test almost immediately. To reach the very top, such a ramp would need a slope gentle enough for teams to haul stones. That slope would force the ramp to stretch for over a mile. The volume of material required to build this single-use roadway would exceed the volume of the pyramid itself, effectively doubling the work for no lasting purpose. Then, after the final stone was set, you would face the Herculean task of dismantling this second mountain of earth and brick without leaving a single trace in the archaeological record. It is a solution that creates a bigger problem than it solves. The zigzagging ramp was proposed as an improvement, a switchback road built against one face of the pyramid. It uses less material but introduces a new and critical weakness. Every time the ramp turns a corner, that corner is left hanging in mid-air, unsupported. As the pyramid grows taller, these unsupported corners become points of catastrophic structural failure, unable to bear the weight of the ramp and the traffic upon it. You would need to build a massive supporting buttress at each turn, which again adds immense complexity and waste. Both external methods treat the pyramid as a passive object to be climbed over, requiring a separate, temporary, and unstable infrastructure that must magically vanish upon completion. Now place the internal spiral ramp beside them. The difference is not just incremental. It is a complete reimagining of the relationship between the builder and the building. The internal ramp does not climb the pyramid. It is the pyramid. It uses the monument's own growing mass as its foundational support, with every turn braced by millions of tons of solid core masonry. There is no separate structure to become unstable. The material required is negligible, just the open space of the corridor itself, which was always intended to be filled. And the dismantling process is ingeniously simple. You do not dismantle it at all. As workers place the final outer casing stones from the inside out, they simply backfilled the now empty corridor behind them with rubble. The ramp vanished by becoming part of the pyramid's solid heart. This is the ultimate in practical parsimony. It turns the greatest weakness of the external theories, the colossal waste of material and effort, into the internal theory's greatest strength. The pyramid constructs and deconstructs its own scaffolding in one continuous, elegant act. Where the external ramp is a separate, burdensome invention, the internal ramp is an emergent property of the design itself. It is the difference between building a ladder to reach the top of a tree and growing the tree with the ladder already inside it. The true legacy of the pyramid is not written in stone, but in the society that imagined it. Accepting the internal ramp theory does more than solve a construction mystery. It forces a profound shift in how we see the people behind the monument. This was not an act of brute force driven by a single ruler's whim. It was the culmination of a civilization operating at the peak of its intellectual and organizational powers. The sheer scale of the project required a level of long-term planning that is almost incomprehensible. A pharaoh would order the pyramid's construction knowing he might not live to see its completion. The architects would design a blueprint for a structure that would take decades to finish, requiring solutions for problems they would not encounter for another 20 years. This is not short-term thinking. It is generational foresight, a society so confident in its continuity and so dedicated to a collective vision that it could commit to a project spanning multiple human lifetimes. Every aspect of the internal ramp system speaks to this deep, strategic patience. You do not build a machine that slowly consumes itself unless you have absolute faith in the process, the plan, and the people who will see it through to the very end. This transforms the pyramid from a static tomb into a dynamic testament to societal endurance, a physical manifestation of a culture's ability to think in centuries, not just seasons. Sometimes the most revealing evidence comes not from success, but from a plan interrupted. While the Great Pyramid stands as a perfected monument, its secrets sealed within, other sites across Egypt offer a different kind of testimony. They are the unfinished chapters, the projects that were halted by time or tragedy, and in their incomplete state, they have inadvertently preserved the very mechanics of their own creation. The Pyramid of Sekhemkhet at Saqqara, for instance, was abandoned early in its construction. What remains is a low, rectangular base, a promise of a pyramid that never rose to its peak. And within that base, archaeologists have found something extraordinary. The fossilized remains of a construction ramp are still in place, not sprawling across the desert outside, but built directly inside the structure's core. This is not a theory or a scan. It is a physical artifact, a ramp caught in the act of being used, forever frozen within the stone. It is a direct, tangible parallel to the proposed internal system at Giza, suggesting this was not a one-off innovation but a standardized method. Similarly, the Pyramid of Meidum presents a haunting silhouette, its outer layers having collapsed in antiquity to leave a tower-like core standing amidst a vast mound of rubble. This catastrophic failure, while a tragedy for its builders, is an archaeological gift. The chaotic debris field is not just random wreckage. Scholars studying the fallen material have identified patterns and features within the rubble that hint at internal passageways and ramps that once threaded through the heart of the building. These sites are accidental blueprints. Where the Great Pyramid succeeded so perfectly it hid its methods, these failed projects became open-air museums, their inner workings exposed by circumstance. They provide the crucial external validation, the corroborating evidence from separate construction, cites that the internal ramp was not just Jean-Pierre Houdin's modern idea, but a very real, practical technique in the ancient Egyptian builder's toolkit. This digital reconstruction was far more than a simple animation. It was a living laboratory, a virtual world governed by the unyielding laws of physics. Houdin and his team could input the exact properties of limestone and granite, the known friction coefficients of wood on stone, the estimated pulling force of a team of workers. Then they could press play and watch a 20-year construction project unfold in minutes. The software could simulate the immense structural stresses as each new layer was added, testing whether the internal ramp design could actually bear its own weight and the traffic upon it. It could model the logistics, calculating how many blocks could move through the spiral corridor each day, how many workers were needed at each stage, and whether the proposed timeline was even feasible. This was not guesswork. It was a rigorous, repeatable experiment conducted inside a computer, a space where you could test 1,000 different scenarios without ever touching a single ancient stone. What emerged was a profound synergy. The ancient problem, defined by physical limits and human ingenuity, found its perfect interlocutor in modern simulation technology. One provided the monumental question, the other provided a sandbox universe in which to search for the answer. For the first time, we could witness the pyramid not as a finished artifact, but as a process, growing and changing in a digital mirror of reality. We could see the external ramp phase give way to the internal spiral, watch the notches at the corners open and close like valves, and observe the grand gallery transform from a quiet hallway into a bustling counterweight engine. This simulation bridged a chasm of 4.5 millennia, allowing a contemporary architect to stand shoulder to shoulder with his ancient counterparts, not through a dusty papyrus, but through a shared language of engineering and spatial logic. It proved that some secrets are not hidden in tombs or texts, but in the very geometry of the task itself, waiting for a tool sophisticated enough to ask the right questions in 3 dimensions. The very design of the internal ramp tells us something profound about the hands that built it. Precision of this magnitude cannot be achieved through force alone. A spiraling corridor with exacting slopes, perfectly aligned loading notches, and a synchronized counterweight system in the Grand Gallery demands more than muscle. It requires minds that can visualize in 3 dimensions, foremen who can orchestrate a one-way traffic flow in perpetual darkness, and artisans who can execute a plan where a single misaligned block could jam the entire system for days. This was not work for an untrained, coerced multitude. It was the domain of specialists. Think of the pyramid not as a prison labor camp, but as the ancient world's most ambitious apprenticeship program. Seasoned engineers would have trained teams in the specific skills needed for each phase, from ramp construction and stone dressing to the delicate art of maneuvering a 50-ton granite beam with nothing but ropes, levers, and physics. The internal ramp theory, in its elegant practicality, inherently argues for a workforce of profound skill and dedication. A slave driven by the lash might drag a stone in a straight line. But a skilled builder, understanding the greater design, would know how to pivot that same stone at a 90-degree corner in a confined space, ensuring the entire project kept moving forward. The monument itself becomes the best evidence for the caliber of its creators. You cannot build a machine this perfect with people treated as disposable parts. The stones would have rebelled, the alignment would have failed, the pyramid quite simply would not stand. Recent discoveries from the desert sands have given voice to this very idea. Just beyond the Giza Plateau, archaeologists have uncovered the remains of extensive worker settlements. These were not squalid prison pits, but organized communities with bakeries producing thousands of loaves of bread, facilities for curing fish, and evidence of medical care. The bones found there show individuals who performed hard labor, but also signs of healed injuries, suggesting they were cared for, not discarded. This paints a picture of a valued, sustained workforce. These builders were likely rotating crews of Egyptian farmers who worked on the pyramid during the inundation season when the Nile flooded their fields. They were compensated with food, shelter, and perhaps a sense of participation in a national project that connected them to the divine and the eternal. This shifts the narrative from one of oppression to one of collective endeavor. The internal ramp theory completes this picture by providing the technical context that makes such a community not just possible but necessary. A project of such layered complexity could only function with a stable, experienced, and motivated workforce. It transforms the story from a tale of a single king's ego into an epic of societal achievement, where the greatest monument ever built stands as a testament not to one man's power, but to the coordinated genius of an entire civilization. The final piece of the puzzle is still hidden from view. While the internal ramp theory connects a stunning array of clues from the corner notch to the big void, the ultimate confirmation would be to see that spiraling corridor with our own eyes. Yet this is the great tension at the heart of modern archaeology. We possess the technology to potentially find it, but we are ethically bound to not destroy the very monument we seek to understand. Invasive digging cutting through the pyramid's core is unthinkable. It would be an act of vandalism against a world treasure, sacrificing the mystery's integrity for the answer. So we stand at a fascinating threshold, armed with brilliant deduction but forbidden from taking the final destructive step. This is not a failure of the theory. It is a testament to our respect for the past. We must find another way to see inside the stone. The future of this mystery, therefore, belongs to the silent observers, the technologies that can listen without touching. Muon tomography gave us our first ghostly glimpse of the big void. The next generation of these scanners could be far more sensitive, capable of mapping not just large voids, but the subtle density variations that would trace the path of a backfilled, rubble-filled ramp winding its way upward. Imagine a three-dimensional map of the pyramid's entire internal structure, rendered in exquisite detail from the outside. Other methods, like advanced seismic scanning, could send gentle vibrations through the stone and listen to their echoes, painting a sonic picture of the interior. Each non-invasive scan is like turning a new page in a manuscript we are only just learning to read. This situation perfectly captures the ongoing dance of historical discovery. A compelling theory can be built from a mountain of circumstantial evidence, logic, and cross-referenced clues long before a single, definitive piece of proof is unearthed or, in this case, visualized. The internal ramp has passed the tests of architectural logic, predictive success, and external validation from other sites. It waits now for technology to catch up to the ingenuity of the hypothesis. This keeps the story thrillingly alive. The Great Pyramid's secret is not locked away forever. It is simply waiting for the right key, a tool yet to be invented by future explorers. The door to the past remains open, guarded not by stone, but by our own growing cleverness and enduring respect. This is where the story of the pyramid expands into a new frontier for discovery itself. Jean-Pierre Houdin did not just propose a ramp, he modeled a new way of thinking about the ancient world, one that fundamentally bridges disciplines. For over a century, Egyptology has been a field built on excavation, on carefully brushing dust from artifacts and translating hieroglyphs. These methods are irreplaceable, the bedrock of our knowledge. But what Houdin demonstrated is that some answers are not buried in the sand. They are encoded in the geometry, the stress points, and the empty spaces of a structure. His work represents a quiet revolution in methodology, the powerful integration of architectural and engineering analysis into historical interpretation. It asks not only what was built but how it could possibly stand, treating the monument as a dynamic problem to be solved rather than a static relic to be catalogued. This shift opens the door to a richer, more collaborative form of inquiry. Suddenly, the conversation around a 4,000-year-old tomb includes 3D modelers, structural engineers, and particle physicists. The Muon scans from the ScanPyramids project are a perfect example of this new synergy. Egyptologists defined the mystery, physicists provided the tool to see through stone, and an architect provided the theoretical framework to interpret the ghostly images that emerged. Each discipline speaks a different language, but together they can translate the silent logic of the builders. This collaborative model is a powerful lesson that extends far beyond the sands of Giza. It suggests a fresh approach to countless other ancient enigmas. Consider the colossal stone heads of Rapa Nui or the precision-fitted walls of Sacsayhuaman in Peru. For generations, the focus has been on the cultural meaning of these sites, which is vital. Yet by also applying this interdisciplinary lens, by asking the practical engineering questions, we might uncover the logistical footprints left behind. How did they transport that stone? What simple machines did they employ? What sequence of construction made this stability possible? The internal ramp theory champions the idea that to truly understand the past, we must sometimes put down the trowel and pick up the blueprint. We must attempt to think like the builders themselves, to see the world through their eyes not as mystics, but as masterful, pragmatic problem solvers working within the limits of their time and technology. This does not diminish the spiritual significance of their creations. It amplifies it. It reveals that their genius was holistic, a seamless fusion of profound belief and breathtaking practicality. The greatest monuments are not just expressions of faith or power. They are the ultimate resumes of a civilization, written not on papyrus, but in the very angles and load-bearing walls that have defied time. By learning to read that language, we do not solve a single mystery. We unlock a new way of seeing every ancient wonder on our planet. The most persistent myth surrounding the pyramid is not about its purpose, but its origin. For decades, a captivating narrative has suggested its perfection is simply too great for the hands that lived beside the Nile. This story whispers of extraterrestrial architects or a vanished civilization wielding technologies we can scarcely comprehend. These ideas are compelling because they offer a kind of magical shortcut, an answer that absolves us from the harder work of understanding. Yet the internal ramp theory stands as a powerful rebuttal to this cosmic speculation. It does not require magic or mystery. It requires only intelligence, organization, and time. Every component of the system, from the lubricated sledges and wooden rollers to the counterweight principle in the Grand Gallery, is built from materials and physics readily available in the ancient world. The genius is not in possessing impossible tools, but in applying known principles on an unimaginable scale. This is a profoundly human achievement. It shows us that our ancestors were not primitive beings awaiting outside help. They were masterful engineers, capable of solving problems of staggering complexity with nothing but observation, logic, and relentless cooperation. To credit aliens or lost super science is, in a way, to diminish the very people whose legacy we marvel at. It steals their triumph and places it in the hands of a fictional other. The internal ramp reclaims that triumph. It places the blueprint firmly back into the minds of Egyptian architects and the calloused hands of Egyptian workers. This shift is not just about correcting the historical record. It is about celebrating a fundamental truth of our species. When we collaborate toward a shared vision, when we combine ingenuity with sustained effort, we are capable of creating wonders that echo through millennia. The pyramid ceases to be an artifact of the unknown and becomes a monument to the boundless potential of human imagination and grit. Its greatest message may not be for the dead, but for the living, a reminder of what we can build when we dare to think in centuries and work as one. There is a profound human need to understand our own story. This unshakable curiosity about where we come from and what we are capable of is the engine behind our endless fascination with the Great Pyramid. It stands not merely as an ancient tomb, but as a direct challenge to our modern sense of superiority. How could people without steel or silicon achieve something we would struggle to replicate even today? This question gnaws at us because it tests the very narrative of human progress. We are drawn to the mystery because, on some level, we need to believe our ancestors were not primitive. We need to see their genius reflected in our own. The internal ramp theory provides the satisfying click of that connection. It is more than an architectural proposal. It is a key that unlocks a door in time, allowing us to step across the millennia and finally meet the builders on their own terms. We are no longer staring at a magical, impenetrable monolith. We are reading a blueprint. We are following their logic, anticipating their problems, and marveling at their elegant solutions. That moment of understanding, that eureka feeling, is deeply personal. It is the thrill of the puzzle piece snapping into place, of the blurred image coming into sharp, brilliant focus. The pyramid transforms from an opaque symbol of lost secrets into a legible text of human ingenuity. And in that transformation, it becomes something even more powerful than a mystery. It becomes a mirror. When we look at it now, we do not just see stone. We see a reflection of our own potential for collaboration, for long-term thinking, and for solving impossible problems with nothing but creativity and determined effort. That is a legacy far more inspiring than any myth of alien intervention or forgotten technology. It is the story of us, written in limestone and ambition, waiting for the right moment to be read. Perhaps the most lasting impact of this idea is not on a desert plateau, but in a classroom. The internal ramp theory transcends archaeology to become a masterclass in applied thinking, a vivid case study for the scientific method itself. Here is a 4,000-year-old problem, clear and monumental. How were the blocks lifted? The first step is observation, looking at the physical evidence without preconception. The second step is to formulate a testable hypothesis. An internal ramp is not a wild guess. It is a proposed solution grounded in the materials and physics of the era. Then comes prediction. If this hypothesis is correct, then modern scanning technology should reveal certain patterns within the stone, specific voids or density variations. Finally, there is the relentless pursuit of evidence. This is where Muon tomography enters the story, a high-tech tool deployed not to prove a fantasy, but to test a logical prediction. The process does not end with a single scan, of course. True critical thinking demands weighing the new evidence against counterarguments. Could the void be something else? Are there alternative explanations for the corner notch? This ongoing debate is not a weakness of the theory. It is the very engine of understanding. For a student, this journey is far more compelling than a list of pharaohs or a diagram of a tomb. It demonstrates that history is not a collection of settled facts, but a dynamic process of inquiry. It shows that the same logical framework used to develop a new medicine or engineer a bridge can be applied to unraveling the deepest mysteries of our past. This makes the story of the pyramid a powerful bridge between disciplines, connecting the curiosity of an ancient architect to the analytical mind of a modern student, proving that the most important tool in discovery has always been, and will always be, the human capacity for reasoned thought. The story of a hidden ramp is no longer confined to academic journals. It has begun to seep into our collective imagination, reshaping how we visualize one of humanity's oldest triumphs. You can now find detailed animations of the internal ramp in major documentaries, its spiraling path rendered in glowing three-dimensional clarity. Respected books on ancient engineering dedicate chapters to dissecting its mechanics. This subtle cultural shift is profound. For generations, the dominant mental picture of pyramid construction was a biblical-scale tableau, an anonymous sea of humanity straining against ropes on a dusty, monstrous slope. It was an image of sheer, overwhelming effort. The internal ramp theory replaces that with something different, a vision of intricate, almost clockwork precision. We now see teams navigating shadowy corridors, executing coordinated turns at loading bays, and operating a grand counterweight system hidden in plain sight. This new narrative does not diminish the scale of the labor, but it reframes it. It adds a crucial layer of intellectual drama to the physical one. The awe we feel is no longer just for the mountain of stone, but for the invisible machine within it, for the brilliant minds who designed a process as majestic as the final product. Our appreciation deepens from wondering at what they built to marveling at how they thought. The pyramid becomes more than a tomb. It becomes the world's most ancient and elegant instruction manual, and we are only just learning to read its pages. That loss of knowledge holds a quiet warning. A civilization capable of such a staggering achievement somehow failed to pass down the very method that made it possible. The secret of the pyramid's construction was not stolen or destroyed. It was simply forgotten, buried not by sand but by the passage of generations. This speaks to the fragile nature of human understanding, how even our greatest triumphs can fade into legend if the chain of teaching is broken. For thousands of years, the pyramid's inner workings were a silent question mark, its builders separated from us by a chasm of unrecorded practical wisdom. Their spiritual beliefs were carved in stone for eternity, but their engineering manual vanished. The internal ramp theory, if it is indeed the key, changes that narrative profoundly. It is not merely solving a puzzle. It represents the recovery of a monumental piece of our collective intellectual heritage. We are not just learning how a block was moved. We are reclaiming a chapter in the story of human problem solving that was thought to be lost forever. This transforms our relationship with the past. History ceases to be a static museum of settled facts and becomes a living, breathing conversation. We are now able to ask new questions of these ancient stones and, through a blend of logic and technology, receive new answers. This ongoing dialogue allows us to pay a different kind of homage to the minds of the past. For centuries, we honored the pharaohs and the gods they served. Today, we can finally begin to honor the architects and the foremen, the problem solvers whose ingenuity turned an impossible vision into enduring reality. By striving to understand their methods, we do more than satisfy our curiosity. We complete a circle of respect, acknowledging not just what they built, but the brilliant human thought that built it. Engineering the ramp was only the beginning of the real challenge. A hidden corridor solves a physics problem, but it cannot feed the thousands of hands that built it, nor can it organize the decades of labor required to see it through. The internal ramp theory, in its elegant precision, forces us to confront an even more staggering reality. The true miracle of the pyramid was not the lifting of stone, but the lifting of an entire society toward a single, generational goal. This level of coordination points to a civilization operating with an economic and political sophistication that rivals its architectural genius. Imagine the sheer volume of resources in constant motion. Beyond the 2.3 million blocks of limestone, the project consumed vast quantities of food, water, timber, and copper tools. A permanent workforce living in those nearby settlements required a daily supply chain of staggering proportions. Archaeologists estimate the bakeries in the workers' town produced enough bread to feed thousands every single day for over 20 years. This was not a seasonal gathering. It was a state-run, industrial-scale operation sustained across multiple reigns. The internal ramp model, with its phased construction and need for absolute precision, reveals why such stability was non-negotiable. You cannot switch from an external to an internal ramp, or execute the delicate counterweight lifts in the Grand Gallery, if the funding or political will collapses halfway through. The project's very design demanded a political system with unprecedented long-term vision and control. The pharaoh was not just a spiritual figurehead, he was the ultimate CEO of history's most ambitious startup, and his administration was the management team that made it possible. This points to a bureaucracy of astonishing efficiency. Scribes would have been tasked with meticulous record-keeping, tracking quotas of stone from distant quarries, allocations of grain from royal estates, and the complex rotation of labor crews. The pyramid was not built on slave labor, but on a highly organized system of taxation, redistribution, and compensated service. Farmers, contributing their labor during the Nile's flood season when fields were underwater, were effectively paid in food, shelter, and a sense of participation in a national project that connected them to the divine. This system transformed a monumental economic burden into a powerful engine of social cohesion and state identity. The internal ramp, therefore, is more than a construction method. It is the physical echo of a political and economic machine, a testament to a society that mastered the art of long-term planning and large-scale logistics centuries before the concept of an empire even existed. The stones tell us how they built, but the organization behind those stones tells us who they were, a civilization capable of uniting the practical and the profound on a scale the world had never seen. Even the most elegant key cannot unlock every door. The internal ramp theory, for all its compelling logic, does not pretend to be a final answer to every question the Great Pyramid holds. It solves the monumental puzzle of the lift, the core engineering challenge, but in doing so, it casts a brilliant light on a host of other, equally fascinating mysteries that still whisper from the stone. These are the details that remind us a civilization's genius is woven from countless threads, not a single strand. Consider the pyramid's breathtaking skin. We know its exterior was once covered in dazzling white Chora limestone, blocks so meticulously cut and polished that they fit together with seams thinner than a credit card. The internal ramp explains how these stones were raised into position, but it does not fully reveal the final, delicate artistry. How were these massive casing blocks smoothed to a mirror finish under the blazing sun? What ingenious scaffolding or abrasive techniques allowed workers to achieve such flawless, seamless joints across acres of surface area? This was a finishing process of staggering precision, a separate chapter of craftsmanship following the brute force logistics of the build. Then there is the human symphony behind the stones. The ramp gives us the blueprint for the machine, but the living, breathing organization of the people who operated it remains a rich field of study. We have evidence of bakeries and settlements, but what was the exact hierarchy on the work site? Who were the foremen shouting instructions in the echoing dark of the spiral corridor? How were shifts coordinated, injuries tended, and morale maintained over decades? The internal ramp model implies an orchestra of specialists, but the full score of their daily lives, their names and stories, is a melody we are still piecing together from pottery shards and burial sites. This is not a shortcoming of the theory, it is its greatest strength. By providing a robust, testable framework for the core construction method, it clears the ground of a centuries-old debate. It allows researchers to stop asking how the blocks got up there and start asking the next layer of profound questions with renewed focus. The ramp is not the end of the mystery. It is the foundational key, the solid platform from which we can now look even deeper. Each unanswered question becomes a new direction for exploration, a specific puzzle waiting for its own elegant solution. This ensures the Great Pyramid will never truly be solved in the sense of being finished. Its story is not a closed book, but an ongoing conversation. The internal ramp theory transforms it from an impenetrable enigma into a structured, decipherable text, with some chapters now clearly read and others awaiting their turn. The wonder shifts from a vague awe at the impossible to a specific, deepening appreciation for the layered complexity of the achievement. The pyramid remains, as it always has, a perpetual source of investigation, but now we investigate with a map in hand, knowing that every new discovery about the polish of a stone or the layout of a worker's town fits into a grander, more understandable narrative of human triumph. Our journey through the hidden corridors of the Great Pyramid story brings us to a powerful realization. The internal ramp theory is far more than a clever architectural guess. it is a complete reimagining of an ancient achievement. We have traced the path from a single architect's digital blueprint to the ghostly images revealed by cosmic particles, from the practical genius of a counterweight gallery to the profound societal coordination it implies. Each piece of evidence, from the enigmatic corner notch to the silent big void, interlocks to form a picture of staggering elegance. This is not a collection of loose clues, but a coherent narrative of human intellect applied on a monumental scale. What emerges is a bridge across time, connecting the pragmatic minds of Egyptian foremen with the analytical tools of modern scientists. It demonstrates that the deepest mysteries are often solved not by finding a lost artifact, but by rediscovering a lost line of thought. The ramp itself may remain physically unseen, sealed within the pyramid's heart, yet its logic now feels vividly present. This theory stands as the most plausible, holistic explanation we have ever devised, transforming the pyramid from an impenetrable symbol into a decipherable masterpiece of engineering. It invites us to shift our gaze. We are no longer staring at a tomb guarding secrets, but at a permanent instruction manual for collaborative genius. It proves that the ancient builders possessed a kind of magic after all, not supernatural but profoundly human, the magic of relentless curiosity, meticulous planning, and shared purpose. If this exploration into one of history's greatest puzzles has captivated you, there are countless more mysteries waiting to be unraveled. Your engagement fuels this journey of discovery, so feel free to share your perspective in the conversation below.